All right, so this is going to be the stats video on the Chapter 5 study guide, which is on probability distributions, Poisson, and binomial as well. And so let's get right into it. It's actually going to be take 2 because the first video had a few errors in it that I wanted to correct. So here we're correcting them. So it says over the course of the year, we have 256 spontaneous combustions. Find the average per day, and then find the probability of having between 2 and 3 in a day. Okay, so remember, for a Poisson, we need two things. We need the average and then the x, the target number of successes. So the average in this case per day, because I'm looking for combustions in a day, we have 256 people combust in a year. A year is 365 days, so we take 256 divided by 365, and we're going to end up with 0.701. Okay? So that's the average. Now, to get between two numbers, this is where it gets a little bit tricky. And we haven't really necessarily done this too much, but we have done the key things about it, so it'll be good to play around with those a little bit here. Right now, we have basically three primary ways of doing Poisson and binomial. We can get an exact number of successes using the PDF. We can get a number or above number of successes using 1 minus CDF. Or we can get a number and below amount of successes, which is with just normal CDF. To get between two numbers of successes, we have to play around with that a little bit. So what we're going to do is we're going to do Poisson CDF of 0.701, comma 3, because this right here will get me everything from 3 down to 0. This will get me the chance of getting from 3 to 0 combustions per day, right, and everything in between. Now, I don't want from 3 down to 0. I want from 3 down to 2. I want to stop right here. I don't want to go any lower than 2. So what I'm going to do is I'm going to subtract this by Poisson CDF of 0.701, comma 1. Now, why 1? Well, because this right here will get me all the probabilities of getting from 1 to 0 combustions in a day on average. Well, if I take from 3 down to 0, if I take all those probabilities and subtract off everything from 1 down to 0, well, all I'm left with is this stuff from 3 to 2. Think about it as like normal numbers. If I have 3, 1, or sorry, 3, 1. Let me try that again. 3, 2, 1, 0. I want this right here. So if I take this entire amount and then subtract off everything from 1 and below, so everything from 1 to 0, well, then I'm just left with everything from 3 to 2. Now you might be saying, well, what about this gap right here? What about from 2 to 1? Because that's not between 2 and 3. And that's true. Technically, we can do like 1.99999 if we want to get as really close to 2 as possible. But I'll show you here in a second that it's not going to change the probability that much. So for instance, if we do this here, I think I still have this saved, but I'll do it again. So second, vars, Poisson, not binomial, Poisson, of 0.701, comma 3, minus of 0.701, comma 1, we get roughly about 15%. So 0.15, or roughly 15%. Now you might be saying, like I said, what about this little gap right here between the 2 and the 1 that's still counted for? Well, if we check here, if I go 1.9999999, if I get as close to 2 as I can, it doesn't change it. In fact, it changes it so small that the calculator can't even notice the difference there, essentially. So it's okay to keep it at 1, even though technically you have a little bit of a gap that you're including there, because that little bit of a gap is negligible in terms of its effect on the probability. So again, the main idea here is you figure out the maximum amount of combustions in a day you want, in this case 3, the minimum amount of combustions a day you want, in this case 2, and you're going to subtract off everything that's below your minimum. In this case, if I want to include 2, the thing that's below my minimum is 1, and so I take away from 1. If I said don't include 2, then I would subtract off 2 as well. I'd go 1 minus Poisson CDF of comma 2, because I want to get rid of the 2, not just the 1. So maximum is your upper bound, the first CDF. The minimum is your barrier, so you do 1 less than the minimum as your subtracting amount to make sure you keep the minimum but lose everything below it. So again, this is a little bit trickier than you might see in a normal test or quiz, but it does help you, again, like I said, play around and use the CDF functions a little bit more uniquely, and it doesn't hurt to poke your brain a little bit and make you think. So is this a distribution? So there's three ways to tell if something's a probability distribution, and they all have to deal with the L2, the probability list. So remember, it's a probability distribution if all the individual probabilities are, if, let me put it this way, if any of the individual probabilities are more than one, it's not a distribution. Well, we don't have that problem here, so we're good so far. If any of the probabilities is less than zero, aka if any of them are negative, it's not a distribution. Again, good so far. And then they all have to add up to 1 or else it's not a distribution. So let me check the sum here. So 0.654 plus 0.043. I don't have high hopes because we have some pretty high probabilities in here, so I'm not thinking it's going to work, but let's see. 0.229. See, we're a little bit too high there. So this would be no, because the sum of the probabilities, P of x, the sum of the probabilities is more than 1. And if the sum is more than 1, it cannot be a distribution. So those are the three things you check. Is the sum more than 1? Is any of them bigger than 1? Is any of the probabilities less than 0? If so, then we don't have a distribution if any one of those three things fails. Now remember, your outcomes can be pretty much whatever they want. You can have an outcome that's bigger than 1. You can have an outcome that's, you can have an outcome that's negative if you want to. It's all a matter of what the probabilities in the table do. Speaking of a distribution, if you want to find the average of a probability distribution, there's the by hand way and the calculator way. So the by hand way says you're going to take all your outcomes, times them by the respective probabilities, get your answers, and then you're going to add up all your products, and whatever you get, that's your average. Right? So you multiply all the probabilities to the outcomes, you add up all your answers, and then boom, you have your average. Now, you can do that by hand. In fact, in this case, it's really not that big a deal. But you can also do it in the calculator. So what you do in the calculator is you go stat, edit, and you enter all your outcomes into L1, like I did here. You enter all your probabilities into L2, like I did there, in decimal form. And then you tell the calculator what you told me. You want to multiply your outcomes to your probabilities. So you want to multiply L1 to L2, and then you want to add up all those answers. So the way you tell the calculator to do that is you go second stat to bring up the list menu. You go over to math, go down to where it says sum because you're going to want to add up all your answers in the end. It's kind of the backwards way of doing it because you have to do the last part first. So you want to sum up the answers to your outcome list times your product list. So think of this kind of like PEMDAS. They're going to do inside the parentheses first. They're going to take L1, the outcomes, times L2, the probabilities. They're going to do that. And then they're going to add up all four answers they get, and we end up with 4.6. So again, you can do it by hand if it's nice enough numbers and it's a small enough distribution. But if you don't want to do it by hand, again, the calculator works just as well. Just like I said, enter your numbers into L1 and L2 respectively, outcomes into L1, probabilities into L2, and then you simply tell the calculator to take the two things, multiply them, and then add them up. It says in a certain 8th grader's dream, 80% of the unicorns have wings. The probability distribution for 5 selected unicorns below. Okay, so find the average and the distribution. So again, we can do this kind of like what we did before. Because it is a probability distribution, we have the table. So we can simply go into, if we want to find the average, we can simply go into stat, edit, and we can do, come on, we can do 0, 1, 2, 3, 4, 5. And then over here, we can enter in 0, 0.006, 0.051, 0.205, 0.410. Whoops, I think I'm out of place here. I wasn't checking. Let me go back up here. I forgot to start at the right spot. My bad. Let's try this again. 0, because I want to make sure my probabilities line up right. 0 to 0, 0 to 0. Otherwise, we'd have a really bad time. So 006, 0.051. Always make sure you're putting stuff in the right spot. 205, 0.410, and 0.328. So I want to get rid of everything below this. There we go. So now I can do the same thing I did before, right? Whoops, come on. I can do sum of L1 times L2. Boom, there's my average. So my average in this case is 4.003. Now my standard deviation is a little bit trickier, or my variance rather. My variance, in calculator speak, it's like this. You want to take the sum, starts the same way, of L1 squared times L2 minus the average squared. To get the standard deviation, which it doesn't ask for, but I'll show you right here, is you want to square root all this stuff here. So you want to square root this, basically want to square root the variance. So you get this number, you square root it, and you get the standard deviation. Now here it just asks for the variance, so we don't necessarily have to do that, but that's how you would do it. So just to show you how that looks here in calculator speak, is I would get the variance first. So I would do, whoops, come on, sum of L1 squared. Don't forget the square there when you're doing the variance, because a lot of people would forget that. Times L2, oops, not L3, L2. Minus, I already have my average, so I could just type that in myself, 4.003 squared, because I got that before. Boom. So my variance is 0.790991. So this is 0.799, oh, sorry, 790,991. And then I can square root that answer. So square root that answer. And I get my standard deviation of 0.889. So 0.889. Again, they don't ask for this, but I figured I'd do it anyway just to give you all three. Now, if I remember correctly, this is a binomial because it says that we have 80% of the unicorns have wings, which means that 20% do not, because again, you either have wings or you don't. There's no in between. So it is a binomial distribution. So just to show you something here, I could have, when I did my list here, I could have entered my L2 like this. Notice how these will not change. I'll show you right now that these will not change. I would go second, clear. Well, actually, you have the list here, so let me show you here. So clear list, these numbers right here, right? Instead of entering these all in, because it's binomial, again, you can only do this with the binomial. I can go in here, press enter, go to second distribution, binomial CDF. My n is 5 because I have 5 unicorns in this table here. I'm going to check up to 5 because it says 5 randomly selected. So 5. My p is 0.8 because 80% have wings. And then I'm just going to press enter. And this did not work out the way I wanted it to. Let me try that again. Clear. Second distribution, binomial CDF. We have 5 selected unicorns, 80% chance of success. And, whoops, binomial CDF, 5 trials, 80% chance of success. This is weird. It should be working here. I'm not sure why it's not. Well, this is interesting. So I thought this would work, but evidently this calculator is not doing the thing here. So sorry about that, folks. I thought I could show you something here, but evidently I am not used to this calculator here. Let me do one more thing here. Binomial PDF. Nope, not going to work for that either. Huh. Okay, well, scratch that. I thought I could do make it all enter in at one go, but evidently not. So I guess we can't do that there. So my apologies there. So let's go back to our regular scheduled programming here. Sorry about that. I probably mistyping a number here, but I don't want to hold you up with the video more than often not. So just imagine that part didn't happen. We'll just go to the next option here. What is the probability of using the above table of selecting 3 or more unicorns with wings? Okay, so if we have the table, we don't have to worry about binomial CDF or PDF stuff. So if I have the table, I want to select 3 or more unicorns with wings. Well, here's 3 unicorns. Here's 4 unicorns. Here's 5 unicorns. I can just add up all these probabilities together and get that. So I don't have to use binomial PDF. I don't have to use binomial CDF. I can just go 0.205 plus 0.410 plus 0.328. Boom. And I get 0.943. So 0.205 plus 0.410 plus 0.328. We add up all that good stuff there, and we get 0.943. There we go. So if you have the table, don't worry about doing binomial PDF or CDF. Just use the table to help you out. Now make sure you're careful with the wording still though, because if it says 3 or more, then that's what we did. If I said more than 3, I would just add up these two, 4 and 5, because 4 and 5 are the only ones here that are more than 3. So again, be very careful on um, putting in your last number or adding up the numbers that you need here. Make sure you read the question carefully and select only the ones that fit the description that I'm giving you. Okay. So again, use the table if they gave it to you because it's a lot easier than doing the other stuff. All right, so a game is played with a bag that contains 8 blue, 2 red, and 1 gold. You bet 10 bucks. If it's a blue marble, you lose. If it's a red marble, you get 8. If it's a gold marble, you get 40. What's the expected value? Okay, so expected value is no different than just saying the average. But in order to get the average, you have to figure out the table first. You have to get a setup here. So over here we have my outcomes. We'll call those x. Over here are my probabilities. We'll call that p of x. Now, let's go ahead and list out all possible outcomes here. So the possible outcomes are you either lose, you win 8, or you win 40. Now, what does lose mean? Because I need a number to put in there. I can't just put in lose here. So lose means that you bet 10 bucks and you don't get anything back. So that's a net negative, right? So losing means I'm going to lose 10 bucks because, again, I bet 10, I didn't win, so I don't get the 10 back. That's what it means to bet. The next two are pretty easy. It says you get a net gain of 8, so that's, again, gaining 8, so positive 8. And then you get a net gain of 40, so that's gaining 40, so positive 40. Now, what's the probability of each thing happening? So you lose if you pick a blue marble. Well, what's the chance you pick a blue marble? Well, there's 8 blue marble out of 8 plus 2 plus 1 is 11. So there's 8 plus 2 plus 1 equals 11 total marbles. So my chance of getting negative 10 is 8/11. My chance of picking a blue marble is 8 out of 11, which is, in decimal speak, 8 out of 11. 0.72 repeating. So 0.72 repeating. If I get a red marble, I get 8. So there's 2 red marbles. So it's 2 out of 11 to get a red marble to win 8. So that's 2 out of 11, which is 0.18 repeating. 0.18 repeating. And then there's only 1 gold marble, so if I want to win 40, I have to pick the 1 gold marble out of 11. So that's 1 out of 11 chance, so 1 out of 11. That's 0.9 repeating, or 0.09 repeating. 0.09 repeating. So how do I get my expected value? I do the exact same thing I did in the last problem to get my average. I take all my outcomes, times the probabilities, and then add them up. That's it. That's all expected value is. So let's get my outcomes first times my probabilities. So I could do this in the calculator in terms of making a table here, but it's just 3 numbers, so we'll do it by quote-unquote hand. So negative 10 times 8 out of 11. I'll just put the fraction form in here. We get negative 7.27. So negative 7.27. I'm going to round to the nearest cent because we are dealing with money. 8 times 2 out of 11. Again, you can do the decimal if you want to. I'm just doing the fraction here just because I like more precise answers. 1.45. So 1.45. And then 40 times 1 out of 11. So 40 times 1 out of 11. We get 3.64, we'll say, because we'll round that last 3 up. 3.64. And so then we're going to add all these answers together to get my grand total average. Make sure you include the negative here, negative 7.27. Make sure you definitely keep that negative because a lot of people forget that. 1.45, 3.64, and I get an expected value of about negative 2.8 or 2.18. Negative 2.18. So if you play this game over the course of a long period of time, on average, you lose about $2.18 a game. Right? If you take all your winnings and losings over the course of 10,000 games, it would average out to be about negative 2.18. Okay? So again, expected value is no different than the average. It's just that when you hear the words expected value, make sure you look for what one is a negative because usually, not always, but usually there's going to be a negative aspect to it somehow because, like I said, this is usually applied to games of chance and stuff like that, gambling and all that stuff there. Right? Make sure I'm still recording here. Okay, good. So next one says we have 15 randomly selected students. The number who select their thumb on average is 8.5 with a deviation of 0.75. Is it unusual to have 11 students who suck their thumb? Okay, So 0.75 is my standard deviation. That's my sigma. 8.5 is my average. That's my mu. So if I want my usual and unusual values, I would do 8.5 plus 2 deviations, so 2 times 7, or 0.75. And then I would do 8.5 minus 2 deviations. Again, add 2 deviations to get your upper bound, subtract 2 deviations to get your lower bound. So 8 plus 2 deviations is the maximum number of usual students I would expect, so about 9.5. And then 8 minus 2 deviations, or sorry, it should be 8.5, not 8. Let me go back and change that. I forgot my 0.5 in there. 0.5. So 10, not 9.5. So 10. And then, excuse me, 8.5 minus 2 deviations, excuse me for that, is 7. So my maximum and minimum amount of usual values is 10 to 7. Anything between 10 and 7 is usual. So is it unusual to have 11 students who suck their thumbs? Well, yeah, because 11's outside here. It's outside the bounds of usualness. So yes, it would be unusual to have 11 students who suck their thumb. I think I got this wrong on the written version. I think I got it, like I said, a few of these wrong on the written version of the study guide, so that's why I'm making this video, to hopefully help correct those. But yes, it would be unusual to have 11 students who suck their thumbs because that is outside the bounds of usual values. Okay. You take a box of seeds and plant them, grow them. You record the heights as less than 5, equal to 5, or more than 5. Is this binomial? Well, right away we know it's not. How do we know it's not? Well, because we have 3 possible outcomes. So no, more than 2 outcomes. In order to be a binomial, you have to have exactly 2 outcomes. So if we just said this, less than 5 or more than 5, then that would be binomial. But if we have a third option, then it no longer becomes binomial. It has to only have 2 outcomes for it to be a binomial. If it doesn't have 2 outcomes, it's not binomial, plain and simple. Okay? A football kicker kicks 70% or makes his kick 70% of the time. He kicks it 220 times. What's the mean and standard deviation? Okay, so we don't have a table here, right? So you might be thinking, how do we get the average? Well, this is binomial because you either make the kick or you don't. And so to get the average for a binomial, there's a shortcut. The average for a binomial is just n times p, or the number of attempts times the chance of success. So he's going to attempt this 220 times in a season, a kick. We expect him to make about 70% of them, because that's his average, or his percent chance of success. And so my average is simply going to be 220, the number of kicks he's going to make, times 0.7, or his chance of success for each kick, and I get about 154. So I would expect him to make about 154 kicks in the season, right, based on his current stats. Now, the standard deviation is even easier, or not even easier, but it's also a shortcut. Instead of doing stuff like I did over here, instead of doing all this stuff, I have a shortcut for the standard deviation if it's a binomial distribution. It's simply root n p q. So root of the number of attempts, 220, times the chance of success, 0.7, times the chance of failure. Well, if there's a 0.7 chance of success, that means there's a 0.3 chance of failure. I get this by just doing 1 minus 0.7 if you didn't know. And so I'm going to go to my calculator here. Square root of 220 times 0.7 times 0.3. Make sure you include the parentheses there. And we get about 6.979. 797. 797. Okay. So again, root NPQ is how you get the standard deviation for a binomial distribution. If you want the variance, it's just NPQ. You just take out the root, and therefore you have the variance. But again, these are shortcuts that just apply to binomials. They cannot be applied to any distribution, just to binomials. What's the chance he makes exactly 200 kicks? Okay, exactly means a PDF. So I want a binomial PDF of 220 tries. We have a 0.7 chance of success. And I want to make it 200 times. Again, my n, my p, my x. And what do we get here? So binomial, second binomial PDF N P X. So we get 4.34 times 10 to the negative 14th. 4.34 times 10 to the negative 14th. So a pretty small chance, which again is to be expected because the average number of kicks we'd expect him to make is 154. And this is about 50 more kicks, about 46 actually more kicks than average. So the chance that he makes 46 more kicks than his average exactly, no more, no less, is going to be pretty darn small. So that small probability there makes sense because he already needs to kick above his average and he needs to make an exact number of kicks above his average. So those two things combined are going to give us a pretty small distribution or pretty small probability of happening there. So if you get really small numbers, don't be afraid. It could just be you're doing a very unusual event, we'd say. Now, these two questions are a little bit of a blast from the past to kind of get ready for finals, essentially. These are stuff we did last chapter about the NPR and CR business and about the ordered probability problems. So here it says an ice cream store allows you to pick 3 toppings from a selection of 15. You can't pick the same thing more than once. How many different combinations can you pick? That's an ugly one there. How many different combinations can you pick? Okay, well, combinations is a C thing, right? So I have 15 things to choose from. I want to choose or combine 3 of them. Because again, it doesn't matter if I choose, say, chocolate syrup, peanut butter sauce, and cherries. But if I choose cherries, peanut butter sauce, and chocolate syrup, that's the same thing. So if I pick peanut butter, cherries, and I don't want to do another C for chocolate, peanut butter, cherries, and strawberries versus strawberries, peanut butter, and cherries versus cherries, peanut butter, and strawberries, all 3 of these are the same combinations. They don't make my ice cream any different. So this is why we're using a combination, not a permutation. If this is a P, that means that each of these 3 things is different, but they're not. Each of these 3 things is the same. The order in which you put them on the ice cream doesn't matter. You still have the same 3 toppings on the ice cream. So if you don't remember what this is, we go 15, math, PBR, or PRB rather, NCR, 3. And we get 455. So there's 455 possible combinations I can make using these 3 toppings, or picking 3 toppings out of 15, essentially. So if I can pick more toppings or pick the same thing more than once, then that will go up. But essentially, if I have 3 toppings, that means I have 455 different combinations I can make out of 15 choices. Now, number 12 says 1 out of every 8 spider bites is lethal and will kill you. What's the probability that if you're bitten by a spider 4 times, the 4th bite will kill you? Now, this is a little bit different than a binomial. You might be thinking, well, isn't this a binomial? Because you either get killed or you don't. There's a binomial outcome. True, but in this case, I want a specific order. I want you to live, 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 die. So if I'm looking for a very specific order for my probabilities, then I'm going to go back to what I did last chapter, which is I have 4 different situations. 1, 2, 3, 4. 1 out of 8 chance of dying. So that means there's 7 out of 8 chance of living. So I want to live on the first bite, live on the second bite, live on the third bite, and then the 4th bite is the one where I want to die. Again, kind of being morbid here, but that's the idea here. Is I want to live, 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 and then die on the 4th one. So 7/8 chance of living, 1/8 chance of dying. So live, 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 die. And I'm going to multiply all these guys together to get the chance of living 3 times and then dying on the 4th one. So 7 out of 8 times 7 out of 8. And yes, there are quicker ways you can enter this in. I'm just going to do it by easy method here. And we get about 0.0837. So 0.0837. Or roughly about an 8.37% chance of living for 3 bites and then dying on the 4th one. That's what this is saying here. So again, slightly different than your average binomial problem because you have a very specific order. Right? Again, these are more reviewish. You probably won't see these on the quiz for this chapter. Maybe it's a bonus question or something. I don't know. But again, this is just making sure you remember the stuff from last chapter because, again, finals, if my pacing is anything like it is consistently, the finals should be coming up pretty soon after this. So I figured I'd put these on here as a little bit of a review. Use the values to find the average, or sorry, to find the range of the max and minimum usual values. Okay, so if I want max and minimum usual values, that means I want the average and the standard deviation. That's why I need to figure out these here. Now, it does look like it's a binomial because I have an n and a p. So remember what we did over here. It's the same exact question. Find your average, find your standard deviation, and then we can find the max and minimum usual values. So my average is n times p. So I have 380 attempts, and I have a 2/5 chance of success. So I'm going to do 380 times 2/5, and I get 152. So my average is 152. And then I need my standard deviation, which is root npq for a binomial. So that's going to be root 380 times 2/5. Now, what's the q? Well, the q is 1 minus p, which in this case is 3/5, but if you don't know that, you can just simply type in 1 minus 2/5. Or if it was like a really nasty fraction, like a really long fraction, you can do it this way, and that will give you what q is. That way you don't have to think, okay, well, if it's 2/5 on this side, then it has to be 3/5 for the q. This will give you the exact same thing. If you just want to type in 3/5, go for it though. So 380 times 2/5 times, down here I am going to type in 3/5 just to be easier. And we get about 9.55. I'll round that up to a 5. So 9.55. 9.55. And so, what's my maximum minimum usual values? So I'm going to take my average. I'm going to add it to 2 deviations. So 2 times 9.55. That's my upper bound. And then my lower bound is my average minus 2 deviations. 9.55. So my calculator here, 152 plus 2 times 9.55. Boom, I get 171.1. That's my upper bound for my usual values. And then do the same thing but subtract. And 132.9, that's my lower bound, 132.9. So these are my max and minimum usual values. Between 171.1 and 132.9, that's what I got. Okay? So again, to find the maximum minimum usual values, you need the average and the standard deviation. If it's a binomial problem, which this is, you can do the shortcuts to get your average standard deviation. If it's just a normal probability distribution, like we had all the way back here, then to get my average and standard deviation, I need to do a little bit more because I don't have the shortcuts. But like I said, it's still doable. It just takes a little bit longer. Okay? But use the shortcuts for a binomial if you have a binomial and you can. Try to guess the card so you have a 1 in 52 chance of guessing a card correctly. Find the standard deviation for the number of times you guess correctly if you guess 30 times. So again, standard deviation. It is a binomial because you're either going to guess correctly or you don't, and we have a set number of trials, 30 trials. So we can use this shortcut once again to get the standard deviation. So the standard deviation is root n, so I'm going to try 30 times here. P, so my chance of success is 1 out of 52. Q, my chance of failure, again, you can do 1 minus 1 out of 52, or just think if it's 1 out of 52 chance of getting it correctly, then there's a 51 out of 52 chance of getting it incorrectly. So again, a 1 in 52 chance of getting it correct, a 51 in 52 chance of getting it incorrect. So I'm going to type this into my calculator here. Square root of 30 times 1 out of 51 times 51 out of 52. And yes, I do know I put in a 1 out of 51. It should be a 1 out of 52. Boom, there you go. Was 51 on the brain there. And then boom, we get 0.7522. So 0.7522. There is my standard deviation for the number of times I guessed correctly out of 30. Okay. If I want the average, again, I just do n times p, so 30 times 1 out of 52, but it doesn't ask for that, so I'm not going to bother with that. I don't want to make the video any longer than it already is. Then the last two here are Poisson. Whoops. The last two here are Poisson. So remember, Poisson needs 2 parameters, an average and a number of successes, if you're doing probabilities. So it says the chance that someone's related to a serial killer is found to be 0.34. After studying 250 people over 10 years, it's found that the average number of people is 8. What's this deviation? Okay, so this one's really easy. If you want the standard deviation for a Poisson, all you do is you square root the average. That's how you get the standard deviation for a Poisson distribution. Because remember, if it's not a binomial distribution, we have to do this long thing here. We square root the variance, which we get by doing this big thing. Okay? If it's a binomial distribution, we sidestep that by just doing root NPQ. But if it's Poisson, well, we don't have an n, we don't have a p, we don't have a q, we don't have a table. We don't have anything for a Poisson other than, as I told you, the average. That's the only thing we need for a Poisson is the average and the number of successes. Well, in this case, we don't really have a number of successes here. All we have is the average. So the only thing we can square root is the average. So we're just going to root 8, and that's going to be our standard deviation. So square root of 8, and we get 2.83 essentially. 2.83, and then we're done. That's it. So to get the standard deviation for a Poisson is really simple. Just square root the average, and then you're done. That's it. Okay? So again, it does say that the chance is 0.34. It says we have 250 people over 10 years, blah, blah, blah. Again, none of that matters. We just simply have the average number of people is 8. We square root the average to get the standard deviation, and then we're done. Okay? Don't need to bother with all that other junk there. So studies conducted sounds that 64 lizards evolved into Godzillas. The probability that okay, so we want to figure out what's the chance that 4 lizards in a day evolve into Godzillas, not in a month. So the first thing we need to figure out is the average number of lizards that evolve into Godzillas a day. So we have 64 lizards in a month. In this case, the month of July, which has 31 days. So 64 divided by 31. So 64 divided by 31 is 0.026, or sorry, 2.06 rather, 2.06. And so I want the chance that 4 lizards evolve into Godzillas. So Poisson PDF, because I have an exact number of successes I'm looking for, in this case 4, of my average 2.06, and I want to check it against 4. So I have an average of 2.06 lizards a day. I want to figure out the chance of getting 4 lizards in a day. So I'm going to go to second distribution, all the way down to Poisson PDF, 2.06, comma 4, and we get about 0.0956. 0.0956, or roughly 9.56% chance of having 4 lizards in a day evolve into Godzillas. What about the chance that no more than 3? Okay, so no more than means 3 or less, right? No more than 3 means 3 or lower. So if it's 3 or less, if I have an or less situation, that means I'm going to be using CDF. So Poisson CDF of 2.06, comma 3. Okay? Because I want to include 3 in here. If I said less than 3, then I would do comma 2, because I don't want 3. I just want 2 and lower. So distribution, second bars essentially, Poisson CDF of 2.06, comma 3, 2.06 rather, comma 3. So this will get me the probability of getting 3 all the way down to 0 evolutions in a day, which is 0.846. 0.846. Yeah, or roughly 84.6%. Which again makes sense because the average is 2. So the most likely individual event is 2.06 evolutions. So if I want everything from 3 on down, 3 down to 0, well, that includes my average 2.06 and all the stuff around it as well. So that should be a pretty high probability because it includes the average in its range. Now, for funsies here, if I said I want the probability of 3 or more, what I would do is I would do 1 minus Poisson CDF of 2.06, comma 2. Because if I want 3 or more, that means I want to get rid of everything from 2 and below. So I would do this right here because this will get rid, minus, of everything from 2 to 0. And then therefore I'll be left with everything from 3 on up. So make sure you remember that. Or more than means you do a 1 minus. Or less means you just do CDF. And then exact number means you do PDF. So that's it for this video. Again, sorry it was kind of a long one there. I had a few things to get through. Like I said, there are some errors on the printed copy of the study guide, so hopefully this video will correct those errors. If you find any more that I didn't get to or that I made a second time, please let me know. Otherwise, have a good day.